at the conclusion of our gathering. I'll put down some scratch if you want it, along with a copy of Quiz 2. Here, some there, and then you pick it up on your way out. Due by, at the latest, tomorrow at the start of our Friday gathering. Got plenty of time. Plenty of resources available. But I do suggest, strongly so, if you want to get the learning benefit derivable from this quiz, even with the special quizzes, you make every effort to work this thing out entirely on your own. That's the way you're going to learn. All right, let's wrap up chapter 18. We have now armed ourselves with all the tools necessary to calculate correctly the concentration of every species which can exist in a water solution. And have a dependency on pH. Equilibrium analysis, K analysis, KW, KA, KB, K for the principal acid-base equilibrium in the system if it should not involve hydronium ion or hydroxide ion, if you're intent on calculating pH, for example. Material balance, charge balance, that's it. So really, K considerations, material balance, charge balance. That's it. With those tools, you can take apart any water solution. No additional tools are needed. So, of course, the responsibility that you have is to understand the tools and how to use them that you have. That's what matters. All right, question 1859. Considers two sulfuric acid solutions. 1.10 molar and one quite dilute at 1 times 10 to minus 5 molar. We are still in pursuit of the issue when, for a charge balance equation, can we immediately set it equal to a charge sum? There's the charge balance equation. Complete charge balance equation involving all charged species for sulfuric acid solution. Here it is. And for most sulfuric acid solutions, this will be negligible. Unless the solution is what? This is sulfuric acid solution. How can this solution be basic? So basic is not the right term to fill in the blank. Quite what? That's it. Because if the solution is quite dilute, the hydroxide ion molarity will be close to the hydronium ion molarity. Smaller, but close. And if the solution is quite dilute, beside M sub I for the solution, and Ka for hydrogen sulfate ion, what else might you need to consider? You're asked to calculate the hydronium ion molarity for a very dilute solution of sulfuric acid. You need the M sub I information. You need Ka for hydrogen sulfate ion. What else might you well need? I'm listening, because this is where the success lies, in understanding what you need to do to solve a problem. No more exists the case where you see a problem and search to find the right formula in which to jam the data. That's gone. Chemistry isn't like that anyway, except for very simple computations. What else might you might need for this very dilute sulfuric acid solution? What else might you might need to consider? What else? I heard it. Louder. Yes! Autoionization of water. Remember? The very dilute solutions we considered, for example, of HCl and sodium hydroxide. Hey, that's going to apply to this too. I told you all, in preparing yourself to be successful on this quiz, to be sure to look at quiz 2 from spring 14. On quiz 2, spring 14, I asked a question regarding the pH. Might have been hydronium ion or hydroxide ion molarity. Who cares? It's still pH. For a 1.0 times 10 to minus 7 molar sulfuric acid solution. If you looked at quiz 2 from spring 14, you remember that. On this quiz, I'm asking 1.0 times 10 to minus 6 molar sulfuric acid solution. You think about that one later. You'll all see it in writing soon. Okay? So back to this. For the 0.10 molar sulfuric acid solution, can we immediately set this charge balance equation equal to a charge sum? Yes? If so, what's the charge sum? Because it was said that you can do it by whoever said yes. Then tell me what the charge sum is. What is it?
0.20?
Absolutely not. Because the ionization extent of hydrogen sulfate ion in this solution is nowhere near 100%. Is it yes, but the wrong reason for yes was given? Or is it no? Because for this solution, you don't know what the hydrogen sulfate ionization extent is until you calculate such. So here, we don't know yet. We can find it out, but you're going to have to do Ka arithmetic for hydrogen sulfate ion. Now, what do you know about the charge sum? Will it be bigger than this number? Will it be smaller than twice this number? Come on, this is the chemistry. Will the charge sum be bigger than this number? You're damn right. Because hydrogen sulfate ion is going to ionize to a measurable extent. So the charge sum is bigger than this number. Now, is the hydrogen sulfate ion ionizing to an extent of 100% in this solution? So how does the charge sum compare to 0.20? Smaller. How about that? Now we're doing the chemistry. We don't know what the charge sum is, but we know it's bigger than 0.10, but smaller than 0.20. Good. Now let's look at 1 times 10 to minus 5 molar sulfuric acid solution. Can you set this sulfuric acid solution charge balance equation immediately equal to charge sum? If so, what's charge sum? I'm listening. I'm sympathetic with you. I know this is the hard part. This stuff isn't sunken in yet. But I'm trying to help it sink in as rapidly as we can have it sink in. Well, let's put the puzzle parts together. For this solution, number one, we've only got one sig fig. Okay? Number two, is this solution quite dilute?
Yes.
But is this solution sufficiently concentrated so that Kw water may not have to be considered?
Yes.
Because this solution, at the minimum, has a hydronium ion molarity of how much? At the minimum. 1 times 10 to the minus 5. And if you do some Kw arithmetic, you'll find out that a solution which has got a pH of 5.0 or any lower pH, forget the autoionization of water. Won't mean anything. You can do the arithmetic for yourself. And that's the way to really learn. However, we know that ionization extent depends on Ka, if it's an acid, and that's the case here. Ka, hydrogen sulfate ion, being 1.2 times 10 to minus 2. A pretty large Ka as far as weak acids are concerned. And what else? What are the two factors on which ionization extent depends? The K value for the acid or base and the molarity. How does it depend on molarity? Directly or inversely proportional? Inversely. Bingo. Now we've done the chemistry. This solution is quite dilute, isn't it? So would you like to make a bet that in this solution, the ionization extent of hydrogen sulfate ion, at least to one significant figure, is 100%? So the charge sum for this solution is what? What is it? What is the charge sum? Well, the first reaction goes 100%. Now the second reaction is going 100%. So the charge sum is equal to the hydronium ion molarity, which is equal to 2 times 10 to minus 5. Done. And I know when we do this, that for many of you are saying, I still don't know how the hell he sees that. I know that. The way for you to see it is to get out your pencil and paper and write this stuff down so that it can talk to you. Right? Prove to yourself that KW doesn't matter, and prove to yourself that at this molarity, hydrogen sulfate ion will go 100%. If my memory is right, to 2 sig figs, hydrogen sulfate ion goes 100% at any molarity equal to or lower than 1.0 times 10 to minus 4. And that's 10 times more concentrated than this. But this doesn't sink in unless you sit down with the paper and do the work. And then you'll say, Eureka, I see it. That's what you got to do. Remember what I told you? First day and many days thereafter. You want to be successful in this gathering? I want you all to be successful. But in order to have the chance to be successful, you got to do what I tell you to do. There's no way around it. All right. Now then, by way of subtopic category, the last special topic in Chapter 18 is for an issue which we've already touched on. But now we'll go back to it in an official fashion. How do we calculate the hydronium ion molarity for a solution in which the main Bronsted-Lowry acid-base equilibrium does not involve hydronium ion or hydroxide ion? Now, first let me bring your attention to an oversight that I made when I wrote the notes. There's this set of notes I wrote 4 or 5 years ago. Okay? I first thought, because I didn't do at that time, I didn't do what I told you just now to do. Sit down with a pencil and paper, write it out. You'd be surprised how much I have learned about chemistry in trying to communicate this wonderful stuff to you folks. I mean it. If you ever have the experience of teaching, you'll find out, wow, you're going to learn big time then. I mean big time. At least if you want to teach meaningful stuff, as opposed to these people who take a general chemistry textbook and read it to the class. They teach nothing. I thought that for any solution like this, where the main Bronsted-Lowry acid-base equilibrium does not involve hydronium ion or hydroxide ion, that we always required, in addition to equilibrium analysis, for the main equilibrium in the system, we always needed material balance and charge balance. I thought that. Wrong. You recall yesterday our looking at particular example illustrating why the statement I just made is correct? In other words, we looked at a system, a water solution system, for which the main Bronsted-Lowry acid-base equilibrium did not involve hydroxide ion or hydronium ion. Yet charge balance, material balance was not necessary to calculate the hydronium ion molarity for that solution. What was that system? What was that solution? We did it yesterday. Or yesterday already ancient history. You now have to make an archaeological dig to find out what happened yesterday. Specifically, the ammonium cyanide solution. And so for the specific case, or additional specific case, of 10th molar to 2,6-fig sodium bicarb solution, my first remark to you is that this solution is subject to material balance and charge balance analysis in the notes. None of which is needed. Because I didn't do, when I wrote the notes, what I just told you folks to do. I didn't analyze the problem and let the results talk to me. So material balance, charge balance, which is provided in the notes in detail for this system, is not required. But at the minimum, from charge balance and material balance for this solution, which is in the notes, we can use the results of the charge balance, material balance equilibrium, along with the equilibrium analysis, which has got to be right, because in that case we're paying attention to every possible angle from which the solution can be analyzed. Okay? That's going to give us the right answer, so long as we don't make an arithmetic goof. That's got to give the right answer. So let's see for this solution how we can get the right answer a lot more expeditiously than involving charge balance, material balance considerations. For starters, which I believe we already noted, I'm sure we have, here's the main acid-base equilibrium. Because bicarb is this very interesting Bronsted-Lowry acid-base species in that, which you see by the appearance of the formula for bicarb in the acid column and the base column of our acid-base table. Bicarb is a stronger Bronsted acid than water, and it's stronger Bronsted base than water. What a unique chemistry. There are some other species which also show this property, and some of the formulas for these other species are in the acid-base table. You can see them. Upshot, in sodium bicarb solution, the PSI tells us the strongest acid present in high molarity is bicarb ion, same for strongest base, so the main BLABEQ is bicarb reacting with bicarb, making hydrated CO2 and carbonate ion. So no hydronium ion or hydroxide ion involved. So clearly we got to go someplace else to get hydronium ion, hydroxide ion. Well, where's the someplace else? Well, pick on this main species, which is the Bronsted acid, or the main Bronsted base species, and consider an equilibrium in which that species reacts with water, because that's a hydronium ion producing reaction for an acid, or a hydroxide ion producing reaction for a base, so that gives us the handle on pH. Hydronium ion molarity, who cares? Same thing. Okay? Well, for bicarb ion, here's Ka, here's Kb. These are, I'm taking right from the new information sheet data. And here, I used to use, and you'll see in the notes, that Kb bicarb is reported at 2.4 as 2.4 times 10 to minus 8, and K bicarb is reported as 4.8 times 10 to minus 11. But later research has allowed me to recognize that this appears to be a better, more accurate value for Ka bicarb, from which, and this appears to be more accurate value for H2CO3, Ka, because in the notes, this is 4.2 times 10 to the minus 7. So based on 4.5 times 10 to the minus 7, I get this as Kb bicarb. I mean, this is Kb bicarb, as opposed to this, what you see in the notes. Okay? So we'll use this rather than this, and this rather than this, and this rather than this, because they are the results of more recent data search which I've conducted. But in doing a problem like this, if you use the information that's in the notes, that'd be fine, because you'd still be getting at understanding the chemistry, and that's what we want. Okay? Now then, we can see or begin to sniff why. From this, the Ka value for bicarb, this, the Kb value for bicarb, we can begin to see why calculating hydronium ion molarity for our bicarb solution is really not difficult at all and does not require MB or CB analysis. That's what we're getting at here. Based on K data, how do we expect the molarity of this and the molarity of this to compare for our sodium bicarb solution? Hint. Do you remember our analysis yesterday of the ammonium cyanide solution? What did we find out about the relative molarities of ammonium ion and HCN? Pardon me, about the ammonium ion and cyanide ion in the ammonium cyanide solution. What do we find out about the relative molarities of HCN and ammonia in that solution? They were equal, weren't they? Do you remember how we were able to determine that those molarities were equal? Because that's where the chemistry lies. For the ammonium cyanide equilibrium reaction, ammonium ion plus cyanide ion, remember we illustrated a K value of 0.90, fraction that went almost 50%? And how did that number, magnitude-wise, compare to Ka for ammonium ion, or KaHCN, or Kb ammonia, or Kb cyanide ion? It was a hell of a lot bigger, wasn't it? The upshot of which is to realize that the only reaction of consequence in the ammonium cyanide solution system which leads to changing the molarity of ammonium ion and changing the molarity of cyanide ion is the equilibrium for which K is 0.90, which means the equilibrium constant for the reaction between ammonium ion and cyanide ion. Let's apply that same thought to what we're looking at here. Is this a big number? If anybody got a push-button calculator, you can take 4.7 by 4.5. I know it's close to this, but I don't know if it's this for sure. If you got a push-button calculator, grind it out right now. Okay? Because this calculation is from these new data points, and I didn't remember to check this arithmetic before I came here to report this to you. In any case, if the value of if 4.7 divided by 4.5 isn't 1.1, I know it's close. What'd you get? 1.04? Oh, well, daggone it, I have to change it. Okay. Okay. But I probably used the 1.04 throughout the calculations to keep my significant figure reliability preserved, and then go back to 2 sig figs at the end of the arithmetic. Okay? Is this a big number? That's a loaded question. Because if I talk about 1.0 times 10 to the minus 4 moles of something, I'm talking about one hell of a lot of stuff. Okay? But how does the magnitude of this number compare to the magnitude of this number? This number is huge next to this number. How about this number compared to this number? This number is huge compared to this number. Not as huge as it is compared to this number, but still huge. What's that tell you? Will this reaction right here, will this reaction result in any particularly significant change in the molarity of this? Will this reaction result in any particular change in the molarity of this? But on a comparative basis, if any of these reactions is going to involve a change in bicarb molarity, which reaction is it going to be? This one, because that's got the biggest K value, by far. All right? So based on this value being much bigger than the other values, we'll play this game. All right? Now then, comes the issue, how do I get this K value? Well, I did it over here. And what you are talking about today in discussion class, pardon me, is an extension of this idea. But this particular idea we've used before. Because when I take this equilibrium constant expression for this equilibrium reaction and multiply by hydronium ion molarity top and bottom, then I have bicarb denominator, hydrated CO2 carbonate up top and hydronium ion up top, which is Ka bicarb, and that takes away this, and this. And then I look at what remains, and I got this up top, divided by bicarb molarity times hydronium ion molarity in the denominator. That's 1 over KaH2CO3. So now I've seen how to evaluate, how to get a number for the K for this complex equilibrium. This complex equilibrium is a composite of two simpler fundamental equilibria. Here they are. Okay? So I get out the acid-base table, put in the numbers, and there's my K value. So that's, again, one of the most important topics you were considering in today's discussion gathering. For those of you who've been there and for those of you who have yet to go there, it's the kind of stuff you're going to be doing, along with other stuff for Chapter 19. Okay? So when we look at this, if it is true that this molarity equals this molarity, because this reaction is the only significant reaction, a reaction of consequence in this system, then we can set this equal to x squared over 0.10 minus x, quantity squared. Take the square root of both sides and solve it for x. Now with this, we will now know the equilibrium molarities. If this calculation is correct, we will now know the equilibrium molarity of this, the equilibrium molarity of this, the equilibrium molarity of this. So can I get the hydronium ion concentration calculated? Boom, zip, quick. Hey, look. Just take Ka bicarb, right? I'll have hydronium ion times carbonate ion divided by this. And from that, I will know this molarity, I'll know this molarity. It's like a one unknown, this. Or you could use this, it doesn't matter. Okay? And from all of this, you'll get a hydronium ion molarity, I believe it's 4.6 times 10 to minus 9. And a pH of 8.34. You can check that. Now then, what will you do to prove to yourself that what we've done here is accurate, correct? You take the very same solution, okay, the sodium bicarb solution, and you attack it with the complete detailed analysis involving material balance as well as charge balance. That's in the notes. And if what we did here is correct, then with the detailed equilibrium with the detailed system analysis, you'll get these same values. And that's it. Now the hard part for you at this stage of the game is to develop a sense of smell as to when I can play games like this and do the calculation correctly. But I don't think that's too difficult, in that if you look at this number and compare it to this number or this number, you see this number's huge compared to these numbers. That's about all you got to do. Okay? When you see the K value for the main acid-base equilibrium, because for any such system as this, the main acid-base equilibrium will always have the largest K value. Because it's the reaction between the best H plus giver and the best H plus taker. It's got to have the largest. It's got to be the largest extent reaction. You do recognize that what K is also a measure of, directly so, is extent. The bigger the K, the larger the extent. Okay? So the extent of this is not large at all, but it's a heck of a lot larger than either of these. All right? So let's take a look at some related systems to help you develop your sense of smell. Okay? How about the hydronium ion concentration for this solution? Is it difficult? If I do the hydronium ion concentration for this solution, do you think I will have to involve, along with pertinent equilibria, material balance and charge balance? You see at a glance for this solution that in this solution, the strongest acid present in high molarity is ammonium ion. The strongest base present in high molarity is sulfate ion. So the main acid-base equilibrium is ammonium ion plus sulfate ion. Do you see that? Good. So we're showing how this solution and the required analysis to get at hydronium ion molarity compares to what we just did here with the sodium bicarb. I repeat the question. To calculate hydronium ion concentration for this solution, you think we'd have to go to the extent of using material balance and charge balance? We can, because that's always going to give us the right answers as long as we don't make an arithmetic foul up. Now I'm going to leave this here because I'm going to want this later. Okay? I repeat the question. Is calculating hydronium ion concentration for this solution fairly simple, or does it require material balance, charge balance? Let's have a vote. Fairly simple. Material balance, charge balance required. How many didn't vote? You don't get any quiz 2 today. Or you can have quiz 2, $20. I'm going to pile up the beer and pizza money real fast. Okay. Well, now let's take a look at the pertinent data. We know the main acid-base equilibrium will be ammonium ion plus sulfate ion. Okay? And that's going to have the largest K value for any equilibrium in this system. But when we want to get a handle on pH for this system, what equilibrium do we have to consider? I'm listening. When you want to get a handle on pH for this system, what equilibria must be considered? Ammonium ion water, because that gives you hydronium ion, and or sulfate ion in water, which gives you hydroxide ion. How about that? So let's look at these. Well, I don't even need to write this stuff down here. We're looking at Ka ammonium ion and or Kb sulfate ion. This we take straight from the table. Okay? This we've talked about previously. Anybody remember what the value is? Well then, that's okay. I don't expect you to memorize these values. I find that kind of learning to be rather pointless. Like turning you into a slave. You don't want that. How do we get Kb for this thing? Kw divided by the value for Ka for the conjugate acid of this stuff, which means 1.0 times 10 to the minus 14 divided by 1.2 times 10 to the minus 2, because hydrogen sulfate ion is the conjugate acid. So we get this. Okay? And from these two data points, you should now be able to answer the question. The question again being, to get hydronium ion calculated correctly for this system, do I need to support a material balance and charge balance? And the answer is no. That's correct. But why is it no? See these two numbers? What does these numbers tell you? They tell you that the ability of this thing to create hydronium ion by reaction with water far exceeds the ability of this thing to create hydroxide ion by reaction with water. Right? Presence of sulfate ion in a solution, practically speaking, has almost no effect on hydroxide ion molarity. So if I want to calculate the hydronium ion concentration for this solution straight away and get the right answer, I only need Ka ammonium ion. And if I only need Ka ammonium ion, I can write, because the equilibrium reaction is ammonium ion plus water makes hydronium ion and ammonia. So I write 5.6 times 10 to the minus 10 equals the hydronium ion molarity times the ammonia molarity divided by the ammonium ion molarity, and set that equal to x squared over m sub I minus x, all done. And if you don't believe that result is accurate, plow through the detailed analysis where you're guaranteed to get the right answer, and you will get exactly the same answer. See, because what I'm attempting to program you to do is to realize that the gap between these numbers is sufficiently large so that you don't even care about this in this solution. Okay? Now let's look at this solution. Okay? Monsters. The monsters are coming. For starters, what do you do first? This solution. PSI. With the PSI before us, we find out that in this solution the strongest acid is ammonium ion. Because Ka ammonium ion is a bigger number than Ka for bicarb, right? And the strongest base is bicarb. Good. I'll leave out the AQ tags just to get at this more rapidly, and I'll use the condensed junky formula for this. And I'll write this, and then I'll write K. And then I'll say, how do I get the K value? Well, we've seen how to play a game. When I see this thing on this side as a reactant and this thing on this side as a product, in my mind's eye already it clicks to me that I can use Ka ammonium ion or Kb ammonia. Either one connects the molarities of these two. And when I see this on this side and this on this side, I immediately know I can use KB this thing or Ka this thing. Either one works. It doesn't matter. Okay? So let's play this game. Now if I play this game, this, Ka ammonium ion, okay? And this is what? 1 over Ka for the hydrated CO2. So I put in the numbers. .5, 4.7, I think it's 4.5. Yeah. Okay? And I do the arithmetic. It's about 1 point something or other. I got it here someplace. Then buddy got a push button grinder, grind it out. When did I write it? There it is. Nope, 1.3, but that's a bigger number. 1.3, 1.2 times 10 to the minus 3? 1.2? 1.2?
1.2 times 10 to the minus 3.
Wonderful. Okay? And now I think, well, this is a heck of a lot bigger than Ka ammonium ion. Okay? And it's a heck of a lot bigger than Ka for bicarb. And it's a heck of a lot bigger than Kb bicarb. Okay, so far? You could look up the data. But if I forget to look carefully at PSI, I'm going to get stung if I take this system and believe that the H2CO3, the hydrated CO2, and the ammonia molarities are equal at equilibrium, and that the ammonium ion and bicarb molarities are equal at equilibrium. I'm going to get stung. I'm going to get bit. And I'm going to be wrong. Because I've forgotten to pay sufficiently careful attention to my PSI. Because in this system, beside this equilibrium reaction, which is the main equilibrium reaction, and the ammonium ion plus water and the bicarb ion plus water as either an acid or a base, there's another equilibrium. And I better pay attention to that other equilibrium. What is this other equilibrium? It's not Kw. What is this other equilibrium? What is this mysterious equilibrium which applies to this system? It exists in this system. And it's got a K value which is close to this. That's why I got to consider it. What is this other equilibrium? What does this PSI tell you? Ammonium ion, bicarb ion. What is the other equilibrium? Yes! Absolutely. So, all right. Also, for which K is equal to. That's why I left this here. 1.0 times 10 to the minus 4. Now, it is true, as we recognize, that that K value is for the best acid and the best base, strongest acid, strongest base reacting. So it's got to be bigger than this K value, which it is. But notice that these K values are kind of close. There's no difference of magnitude of 1,000 or 10,000 or anything like that. Upshot, if I calculate the hydronium ion molarity for this system based on this only, and then Ka ammonium ion or Ka or Kb bicarb, because I would be taking the molarity of this and the molarity of this to be equal in equilibrium, I will be close to the right answer, but I'll be wrong. Okay? And therein lies the problem. So, if you set about doing the analysis, because this one you need MB and CB. This is a tough calculation. I mean, much tougher than what we've so far considered. Because you need MB and CB. So if I asked you to do a calculation for something like ammonium bicarb solution, I'm never going to ask you that on a in-class quiz or an exam, because you haven't got time to do the arithmetic. I wouldn't ask you to do the calculation. But I would certainly ask you questions about why do I need MB, CB here, and I'd ask you about K magnitudes and stuff like that. Because at equilibrium for this solution, how must the ammonium ion and bicarb molarities compare? How must they compare? For this solution at equilibrium, how must the molarity of this compare to the molarity of this? How must they compare? Because if they're not equal, which they are not, one is bigger than the other. Between these two. At equilibrium for this solution, which species has the higher equilibrium molarity? Ammonium ion or bicarb ion?
Bicarb.
I heard a vote for bicarb. It's one or the other, that's for sure. You know, so if you make a vote, you're 50% of the time you're going to be right. And you know how much credit I'm giving you for a vote? Nothing! I don't care about votes. Science is not done with politics, thank goodness. If I sent this to Congress, they'd go into a huddle for about 3 years. And still not have an answer. Or the wrong answer would be one or the other. Then there'd be a bunch of hate letters in the mail about how Obama's doing a terrible job because he messed up this problem. How must these molarities compare? All right, I'll tell you the answer. Now you tell me why the answer is correct. Because you know you're being programmed to be the people who always answer the question why. Because when you can answer why, then you know what's going on. And until you can answer why, you don't know what's going on. It's as simple as that. Why is this true? In this system, ammonium ion in the main is being consumed by this reaction. Right? But in this system, two reactions are doing an effective job of consuming bicarb ions. This one and this one. These both chew up bicarb ion. But only this chews up ammonium ion. Beside ammonium ion plus water, and that's 5.6 times 10 to minus 10. That's nothing compared to these in terms of magnitude of ammonium ion chew up. So now you know how to tell me how these compare at equilibrium. Now I'm listening. Is this bigger than this, or is this bigger than this? That's what I'm hearing. Which molarity is bigger? Which molarity is bigger? Hydrated CO2. You agree? Because the first reaction makes hydrated CO2 and the second reaction makes hydrated CO2. So you got two reactions of consequence making hydrated CO2. But you only got one reaction of consequence making ammonia. How about that? Isn't it amazing what you can do with this stuff if you let these numbers talk to you. And that's the kind of stuff you're supposed to be doing in these math classes. I mean it. Because in science, you have to think numbers all the time. All the data with which we deal are obtained by measurement making. You know that. Wonderful. So this is the toughie, because you need material balance, charge balance, support. All right? Now we got one more solution. How about this one? Because now you have all the tools at your fingertips to crack any water solution regarding species whose existence depend on pH. Well, when I glance at this solution, okay, and I write this, again, I'm leaving out the AQ tags and stuff to get at this more expeditiously. I got this. This certainly applies. Okay so far? But based on what we have programmed you with, at least I hope successfully so, is there another equilibrium system that you must consider to solve this puzzle? I'm listening. Because this is the hard part. This is the chemistry part. I mean, I have a student, sometimes they come into my office with a problem like this and they say, tell me what to do and I'll solve the problem. No, you tell me what to do, then you solve the problem. Because I got to program you to figure out what to do. Knowing how to do it is not nearly as difficult as figuring out what it is that you have to do. That's the chemistry part, that's the hard part. So beside this equilibrium, is there another equilibrium of consequence that we must consider to solve this puzzle? Come on, let the data talk to you. Yes! Isn't it a very dilute solution? Goody. Uh-oh. So, how many unknowns we got? We don't know this one, do we? And we don't know this one. Question? With material balance, if I know this one, will I know this one? Or vice versa, with material balance, if I know the equilibrium molarity for this, can I know the equilibrium molarity for this? You're daggone right, because I know this for sure. Right? There's MB coming into play. So far I'm looking at two unknowns. Now back to this one. The value for this, of course, is the same as the value for this one solution. I've had some interesting students have told me, well, I got two different solutes, so in my solution I got two different pHs. Well, that's quaint. One solution having more than one pH. Well, that's interesting. If I know this, is this an unknown? Heck no! Because this is kW divided by this one. Okay? So this is not an unknown. So I now got two equations and two unknowns. Can I solve? I got two equations and two unknowns. Can I solve? Absolutely. But I'll tell you, by taking advantage of charge balance, you can solve this quite expeditiously, as opposed to dealing with it from the strict algebra approach of having two equations available and two unknowns. You apply this. Always keep your tools ready to use. And when they make things more straightforward, more convenient, use the tools. Why does application of this make solving this simpler or more direct, more expeditious approach than treating this from the strict algebraic standpoint of two equations, two unknowns? Let's write CB for this system on your paper right now. It's not difficult. It's a simple CB system, or a simple system from a CB standpoint, I should say. Come on, let's put it to use. Right now, let's go. Quick. In this system, my very dilute acetic acid solution, what's the only positive ion? What is it? Hydronium ion. And in this system, how many negative ions do I have? 2. Well then, let's write it. All right, there's CB. Now let's rewrite this CB. Nothing fancy about this, right? Great. So, can I take this expression? Okay. And rewrite it so that it has either acetate ion in it as an unknown or acetic acid by using material balance? Huh? Yeah, right? Up here, I can put, I won't use this, I'll write instead 5.0 times 10 to the minus 7 minus the acetate ion molarity. Bingo. Or if you want, I'll keep this in, and up here I'll write 5.0 times 10 to the minus 7 minus acetate ion. Acetic acid, here, I'll put it in up here for acetate ion, and I'll write 5.0 times 10 to the minus 7 minus HAC molarity. Okay? And keep this in the denominator. Okay? Now what am I going to do with this? In other words, can I take this equation and turn it into an equation which only got one unknown in it? Huh? With this? With this, can I solve for acetate ion in terms of hydronium ion? Huh? Hydronium ion is equal to this plus acetate ion. So acetate ion is equal to hydronium ion molarity minus Kw divided by hydronium ion. So I can put that in for this. And all of a sudden I got one equation but one unknown, hydronium ion. That's what I want to calculate. Done. The rest is use up some pencil and scratch paper. That's it. We've now shown you the whole ball of wax for chapter 18. Perhaps you thought we'd never get through chapter 18. But now we have. And now you've got all the tools necessary to take apart any water solution. So as again, to be able to determine correctly the molarity of any species in the system whose life depends on pH. How about that? Now then, a few remarks on chapter 19. This is kind of clumsy because some of you have heard about this and a few of you have not yet heard about this. But for chapter 19, let me say this to you. We're now dealing with equilibria, KSP equilibria. KSP equilibria are equilibria which apply to equilibria established by dissolving a material in water which isn't particularly soluble in water, specifically ionic compounds. Those are the only types of semi or partially soluble materials that we will consider, ionic compounds. All right? So let's go back and revisit in brief an equilibrium system that we prepared on day one, if you can remember back that far. Calcium carbonate. Obviously, one of teachers' favorite weapons, right? Because this piece of chalk is mainly calcium carbonate. Here I've taken earlier on some deionized water from our DI tap over there. Where did I put my scooper? Scooper, where are you, scooper? I forgot to bring the scooper. I don't see it in the back. Ah ha ha! I hid it from me. Okay. Powdered calcium carbonate. Again, we're repeating what we did our first class gathering when we were talking about equilibrium systems, which we are still doing. But again, now we're in pursuit of learning how to deal with equilibrium systems that involve ionic compounds that aren't very soluble in water, like calcium carbonate. Okay. All right, well, we see after some vigorous shaking, the system is quite cloudy because there's a bunch of undissolved calcium carbonate particles distributed throughout the liquid phase. But since calcium carbonate is more dense material than the solution part of this mixture, on standing the calcium carbonate particles will settle to the bottom. You can see already at the top the system beginning to clear the calcium carbonate particles because they are heavier or more dense sink to the bottom. Heavier or more dense? Okay. I always kind of got a kick out of students who told me, for example, that pennies sink in water because they're heavier than water. I'm going to give you one penny and have you measure its mass, and then I'm going to send you over to the Pacific Ocean and have you measure its mass and see which sample is heavier. Okay. But the issue here is things are dangerous. An issue, I remind you, we brought to your attention on day one and made mention of the considerations we have to make to deal successfully with analyzing a calcium carbonate saturated solution system with water being the solvent, because that's the system we just prepared. The question is this the only equilibrium? Well, nevertheless, we can take this equilibrium and use it as an expression of KSP calcium carbonate. Because KSP for a salt of limited solubility in water, which for you folks have already had discussion in class, and which for all of you if you've looked at chapter 19, which I told you to do. you recognize that KSP is by definition the equilibrium constant for the equilibrium established when a semi-soluble salt written as a reactant is in equilibrium with the particles put in the system with water being the solvent. So KSP is really the equilibrium constant for the reaction that occurs when a solid is dissolved into water to achieve saturation. Okay? So not all the solid will have dissolved, just like for the system we just made. Okay? So for this system, we can use this as a definition of KSP calcium carbonate. But, to repeat something we did day one. Now I hope this works, because sometimes this DI water is pretty acidic and I have to run a whole bunch of it out of the tap before I can get the appropriate results. Oh, we're doing fine. Phenolphthalein is the indicator. A distinct red-pink color is developed on treatment of our saturated calcium carbonate water solution with phenolphthalein. And phenolphthalein, again, if you don't remember, becomes this red-pink color at pHs above 9.2. And this is a good deal above 9.2, because this is distinctly red-pink. Or perhaps you wish to call that lipstick red. I don't know. I don't care. Okay? But what is this observation telling us? It's telling us that in addition to this equilibrium, when we dissolve the calcium carbonate in water, what species did we produce? Why did this become red-pink? Why did the pH go up? Because we made hydroxide ion. So guess what? K for this equilibrium is also a legitimate calcium carbonate KSP expression, because it reveals the chemistry that occurs when calcium carbonate dissolves in water. Now, for most but not all cases, you can use this as KSP. But there are cases where you can't use a reaction like this. You have to pay attention to reaction with water. Like silver sulfide dissolving in water, because sulfide reacts with water to 100% extent. So if I write Ag2S in equilibrium with silver ion and sulfide ion, I've written a fable, because there ain't no sulfide ion in the system. So you got to be careful about that. So this kind of stuff we're going to deal with in chapter 19. One more remark. The first part of chapter 19, which you folks looked at in discussion class, and which you folks who are still going there will look at, is dealing with solubility calculations for equilibria involving semi-soluble salts, for which hydrolysis, reaction with water, doesn't matter. Those are the simplest cases. But when you get to this, the system gets more complex. And this is where we will be tomorrow. Now, hang on, sit tight, so I can stack this stuff places and have you folks pick this up without running me over.